In this video, I'll go through the workflow to create 3+2 or positional 5-axis toolpaths from simple 2D to more complex 3D finishing operations. Often the most difficult part of learning 3+2 in Fusion 360 is accepting how simple it is. Essentially, I'll be using a tool orientation parameter to position the tool relative to the part and then applying typical 2D and 3D principles to create the toolpaths. Using the setup from the previous video, I've created a couple of preliminary operations to first square up the block of stock and then start roughing away material using the work coordinate system orientation from the setup. If I run a stock simulation of these starting operations and skip to the end of the toolpath, I can see that I need to finish this angled face on the top of the part, and that there's a good amount of stock to remove on the side angled face as well. While these areas would require multiple setups to reach using traditional 3-axis strategies, I can use 3+2 to access them much more easily. I'll start by using a face operation to finish the angled face on the top of the part. The face mill is automatically selected, so I'll move on to the Geometry tab where I'll define the stock contour. The contour is automatically projected on the XY plane, and this is a nice, clear, visual indication that this toolpath is currently using the work coordinate system orientation from the setup. To adjust the orientation of the toolpath and effectively create a 3+2 toolpath, I'll check the tool orientation checkbox. This opens options to define the toolpath orientation that look very similar to defining a work coordinate system in a setup. I'll set the orientation for this operation by defining the Z-axis using the face to be machined. This selection defines the direction the tool will point, and the X and Y axis definition happens on the back end of the post. For more on how this is handled on the back end, check out the orientation definition video. Moving on to the Heights tab, the current orientation is clear as all the height planes have adjusted. I'll make the bottom height the same level as the stock contour selection. I want to note the X direction of the tool orientation, since pass direction is relative to the X axis. I'm okay with the passes going along X as it's defined, so I'll click OK. The toolpath generates at the specified tool orientation, and I can see in the preview that the tool is pointing opposite the Z axis as expected. I'll use the same workflow to add a 3D adaptive clearing to rough out the material left on this angled side of the part. I'll select the right roughing tool, then move on to the Geometry tab to define the tool orientation by checking the box and defining Z using the flat angled face. It can be beneficial to start out with tool orientation, since this redefines the rest of the selections, generating more accurate contour selection previews. I'll create a machining boundary selection to contain the toolpath to just where the stock remains, and then enable rest machining from previous operations. I'll check the cutting parameters in the Passes tab for this tool, and then click OK to generate the adaptive clearing. From the preview, I can see that the toolpath is triangular in form, like the stock that has remained, and is only covering most of the face. This is the rest machining at work, keeping the toolpath contained to the productive areas. Lastly, I'll generate the finishing pass for these faces. Just like the first step, I'm going to create a face operation, define the tool orientation, making Z perpendicular to the face to the machine, and define the stock contour as the edge of the face. To finish the curved portion, I'll use a 3D parallel operation, also with tool orientation applied. I can create this 3D parallel by deriving it from the adaptive clearing operation, which preserves the tool orientation along with many other parameters as much as possible. I'll choose a more appropriate 3D finishing tool, adjust the machining boundary to just cover the curved face, and enable contact point boundary. Finally, I'll adjust the step over and generate the parallel toolpath. Now that I've explored using tool orientation alongside general 2D and 3D concepts to create 3+2 toolpaths, I'll look at how to increase the accuracy of stock simulations in multi-axis machining.